Hello students, welcome to Sri Jayendra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 6 of our unit, Thermal Properties of Matter. So let's begin with today's class. In today's class we are going to discuss about the radiation. So let's begin. In the previous class, as you are aware, that we have already covered the convection and and the conduction process to transfer a heat from one place to another. This is the third method to transfer a heat from one place to another. So let's begin with the radiation. When we say radiation, it is the process of transmission of heat from one place to another without the necessity of the materialistic medium that we call as a radiation. So it can transfer a heat from one place to another place without having requirement of medium as well, and that process is known as the radiation. Look, that we are receiving an energy from the sun. Yes, that is the process of radiation, that between sun and between earth there is a very long region would be there where there is no atmosphere, and even in that region the heat that has been developed by the sun is transferred to the earth even though no medium is there. This is sometimes what we call as the electromagnetic waves. They are the waves which does not require any medium to travel. I hope this is clear. So in this process, heat transmits in the form of an electromagnetic radiation. Yes, so it is the radiation by virtue of its temperature, that is what we call as a thermal radiations. And very important aspect is all bodies emit thermal radiation except at absolute zero. That means when they are at above zero, whenever they are at above zero, they are going to transmit or they are going to receive. So let's begin. One of the theory that has been given by Prevost, he is the scientist. He has given certain theory that is called as a Prevost theory of heat exchange. He said that according to the Prevost theory of heat exchange, that all bodies emit the thermal radiations when they are at above above absolute zero temperature. This is the situation, that all bodies they are going to emit thermal radiations when they are at above absolute zero temperature. This is Prior's theory of heat exchange. But one of the application of this is that, please mind this all statement. These are very important statements, that all bodies above 0 K transmits as well as receive the energy. So all bodies above 0 Kelvin transmits as well as receive the energy, and this transmission or receiving the energy feels us that this object is colder or this object is hotter. Now let's understand this with the example. Let's suppose the situation is, these are the ice cubes. These are the ice cubes, and let's suppose here you as a person is standing. So when you when you touch the ice cubes will give you the energy, let's suppose 10 joule. But you as a person is giving the energy of 1000 joule. So basically we are losing 990 joule net energy. So we feel ice cubes colder. A same way, let's suppose a flame is there and you are standing as a person over here. I'm sorry. In this situation, you as a person giving the energy of 10 joule, but you are receiving an energy from the flame that is of 1000 joule. So it is a gain, of plus 990 joule. That means we feel hotter. I hope now you understand how does we feel hotter and how does we feel colder. So it is absolute relations. It is absolute relations and it is absolute observations that when our body loses certain amount of energy, we feel colder. And when our body when our body gain certain amount of energy, we feel hotter. It is as simple as that. I hope this is clear. Do you understand this? That this is the basic reason, this is the basic principle behind anything that we feel that this one is the hot object, this one is the cold object. This is the as simple as that. That if we receive net amount of energy, if we receive, that means another body is at higher temperature and we feel the hotter. And if we losing net amount of energy, if we are losing net amount of energy, that means that body is at lower temperature and we will feel a colder when I'm going to touch it. Is it clear? Is it? Are you sure? Are you? Great. Now let's understood a different aspect. That let's suppose this is one of the object, and on this object we are giving a q amount of energy. Within this qa has been absorbed. Q is the total energy. Within this qa is the absorbed energy. Qr, this is reflected energy. And this qt, it's a transmitted, or I should say it's an emitted energy. I hope this is clear. So I am having a total amount of energy, let's say it's a q. Within that it has been divided into three parts. Certain amount of energy has been absorbed, it's a qa. Certain amount of energy from this q has been transmitted, and certain amount of energy has been reflected. So it has been divided into three segments. Q is divided into three segments: qa, qr and qt. So what I can write, it's a q is equals to qa plus qr plus qt. I hope this is clear. Yes, no, yes. Now now let's divide this by q, it's which is a total amount of energy. So what I'm going to do is I'm going to define three parameters. One, qa by q, that is represented by a, and this is absorbent. QR by Q, that is defined as R, it is a reflectance, and QT by Q, that is, let's say, represented by small t, this is transmittance. So in this situation it is equals to 1, that is equals to QA by Q, which is equals to A, QR by Q, which is equals to R, plus QT by Q, this is equals to T. So this can be written as 1 is equals to A plus R plus T. This is the total situation. I hope this is clear. Is it clear? Is it? So if any body is having if anybody is having t is equals to 0, let's say if anybody is having t is equals to 0, then what would be the situation? That we have this relation, it's an A plus R is equals to 1, where A is the absorptance and R is the reflectance. And we have put that, we have considered that, let's suppose my body is having t is equals to 0. If this is the situation, then what I can write is the A is equals to 1 minus R, or or R is equals to 1 minus A. I can write this. Do you understand this? Do you? Yes, that could be written as equals to 1 minus R, or R could be written as R is equals to 1 minus A. So this is mathematically absolutely correct, but what its physical significance? Let's try to understand this, that certain body is there which is having an A of 98 percentage. That means it is having an R of 2 percentage, or let's say another body is there which is having an R of 97 percentage. That body is having a of 3 percentage. So what does it significant? What these statements show to me? So what I understand is that a body which is good absorber of an energy is poor reflector of energy. A first statement. We will discuss it, but let's look first a second statement. A body who is very good reflector is poor absorber. Do you understand this? What does it mean? Look at this. This body absorbs 98 percentage of total energy available. First thing, its a transmitting capability has been 0. If transmitting capability has been 0, this is at 98 percentage. So if it absorbs 98 percentage of energy, then it can reflect only 2 percentage of energy. So a body which is very good absorber of an energy is very poor reflector, because it can absorb 98 percentage, and when it has absorbed 98 percentage of energy, it can reflect only 2 percentage of energy. So is poor reflector of energy. I hope this is clear. One more thing, it's that, let's suppose a second example, second object is there that can reflect a 97 percentage of energy. So if it has been reflected 97 percentage of energy, it can absorb only 3 percentage of energy. So a body who is very good reflector is very poor absorber. I hope this is clear. Is it clear? Is it any doubts, anything? Are you sure? Do you have any doubts? Is there anything? No? Okay, one more thing. One more thing. Let's understood the situation. Let's suppose this is one of the room, and in this room we have two spheres that has been hung by with the help of a string. And let's suppose this surface of this sphere has been colored with black, and this surface is having a shiny surface. It has been painted so that it can have a shiny surface. Now let's suppose from the external I have given 100 joule energy to both. Now the question asked is that, let's say this is a first body, this is a second body. Which body does have higher temperature? This is your question. Take your time of 20 seconds and think for this, that what should be the, which one would be at a higher temperature. Yes, what was your answer? What was your answer? Your answer may be that, sir, a body temperature 1, a body of temperature 1 should be higher than the temperature of the second body. Is it yes? Yes. If this is your answer, this is absolutely incorrect. This is not the case. Why? Now, understand the situation that when no corona were there, you were sitting in the classes, and you were studying the subjects. When you all were sitting in the classes, let's suppose assume that you have wear a black colored jacket and your friend has wear white colored jacket. So is it so that you have wear as a black colored jacket, your temperature would be higher, and as your friend has wear a white colored jacket, that means it's his temperature would be lower? Is it so? No. If you and your friend are sitting in a same room, if you and your friend are sitting on a same room, that means temperature of both of you would be approximately equal. I'm telling approximately. Yes. So there is very nearer. This temperature of you and your friend is very nearer. So it is the same case. But now the confusion arises that as we have learned in this in these previous classes as well, that black colored absorbed very well, and the shiny surfaces can reflect very well. So if it has absorbed, if if it is absorbed in a very good manner, then its temperature must be higher. Why it is not at higher temperature? So the thing is, those objects which are very good absorber, which are very good absorber, are very good emitter too. So those who can absorb very well, they can transmit or they can emit very well as well. So it is fact that when I have given 100 joule energy to both of them, a first object has absorbed a very good amount of energy, and this has reflected its most of the energies. But when this first object has when this first object has received a good amount of energy, it has also transmitted or it has also emitted that certain amount of energy to the surroundings to make it cooler or to arrange itself to a room temperature. So, from a conclusion of three conditions, what I understand is that A would be equals to E. If your A is higher, that means yours R is lower. That means if you are very good observer, you are very poor reflector. And if your A is higher, your E will be higher. A is equals to E. If A is lower, that you are if you are very poor observer, that means you are very good reflector. Yes, this statement, this is the summary of the total statements that we have delivered up till now. Do you have any doubts up till now? Is it clear? Is it clear? Are you sure? Any doubts? Is there anything? Any doubts? Is there? No? Great. Now let's look at the emissive power. What it is. We can say that it is the amount of energy emitted at a given temperature for a given range of wavelength, let's say from lambda to lambda plus d lambda, by a body per unit area per second. So it is the amount of energy emitted at a given temperature for a given range of wavelength by a body per unit area per second. It's basically a energy divided by area into time. Yes, so it's an energy by time divide by into area. So this is joule per meter square into second, or this energy by time could be written as watt as well. So it's a watt per meter square. Dimensional formula of it, it's an m1 l0 t to the power minus 3, or we can write even this as a energy flux. This is dE lambda is the energy emitted per second. I hope this is clear. Now, what energy flux? It is the energy flux by a body within wavelength range of lambda and lambda plus d lambda is proportional to the wavelength interval, and this could be written as dE lambda, which is energy flux directly proportional to the d lambda, and this is equals to, if I remove the proportionality constant, I can add the constant where E lambda is the emissivity. It is the emissivity of the body. Now the again question arises, sir, what is emissivity? So let's have a look. We can say emissivity E lambda is the ratio of the emissive power of a body to the emissive power of the black body at the same temperature. This is basically emissivity, which is ratio of the, it's an emissive power of body or object to the emissive power of black body. So it's an emissive power of a body divided by emissive power of a black body, and as it is a ratio of the power to the power, it is a dimensionless quantity, and the value of the emissivity varies between 0 to 1 for black body. For black body, emissivity is equals to 1, and for perfect reflector, that means an object who is going to reflect 100%, for them emissivity would be 0. Human emissivity is about zero point 0.9, it's a 0.97 if you observe the exact figure. I hope this is clear. Is it clear? Is it clear? Now the question might arise in your mind that, sir, everything is okay, but what is black body? What is black body, and how can I define that this is black body? What do you understand by black body? Tell me, what do you understand by black body? What do you mean, or what do you understand when I use the word black body? I can say that black body is the object which can absorb and emit energies of all wavelengths or frequencies. Yes, so it is something that can absorb everything that has been delivered to it. And not only it is the case that it is going to absorb only, it is going to emit as well. Yes, so we have learned previously that those objects who are very good absorbers are very good emitters too. So those objects who absorb well, they emit well. It is the case of the black body that this can absorb the well and this can emit the well as well. I hope this is clear. We have one of the practical model of black body that we call as the Ferry's black body model. It is something like this, that let's suppose we have certain slope kind of thing over here. Yes, and from here as light energy will come. We have painted this walls. We have painted these walls with a black colors. So light has been came from here. It is going to be reflected to here. It is going to absorb that here. But it is not the case that in a one reflection it is going to absorb it completely. So due after the multiple reflection, after approximately 615 to 16 reflections, this is going to completely absorb. So this is the first situation, that this a light has arrived and it has absorbed it well. Now now when this is heated, it can emit it can emit all those frequencies which it has absorbed. I hope this is clear. So it is going to emit all the frequencies. It is going to emit all the frequencies which it has absorbed. This is the black body model. For ideal black body, for ideal black body, E should be equals to 1. I hope this is clear. Is it clear? Is it clear? For ideal black body, E should be equals to 1. Now, what should be the color of black body? What should be the color of black body? What do you think? It is not necessary that black body must be black in color. It is not at all required. So very surprising, but yes, it is true. It is not necessary that black body must be black in color. You can have one more statement that surprise you. Sun is perfect black body. And you now understood that sun, we observe it as an yellowish color or orangish color, but it is not in black in color, that is for sure. Yes, either you consider it as a yellow color or a dark yellow or orange color or anything, but it is not black, that you accept. So sun is perfectly black body. For sun, E is equals to 1. Yes. So when they use to what that sun is delivering this energy, we are going to use emissivity as a 1. Please do remember this. And one more thing. So some examples of black body are lamp black or Soot. These are the examples of the black body. So I hope you are now understood fully that what black body is and why do we use it, that what is emissivity and everything. Are you clear with this? Are you? Are you sure? Great. Now let's understand the absorptive power. We have understood the emissive power, we understood the emissivity, and from the emissivity we need to switch to the black body. Now let's understood what is absorptive power. Basically it is the ratio of the energy absorbed in a time to the total energy incident on the body during the same time. So basically it is a ratio of the energy absorbed. Let's write this. It's an energy absorbed in a time, divide by it's a total energy incident on the body. This is the total energy incident on the body. This is the absorptive power. The absorptive power of a black body, the absorptive power of a black body is equals to 1 because it is going to absorb everything. If it is going to absorb everything, that's why it can emit everything. Platinum black or the lamp black or the carbon black approximately behave like a black body. And the absorptive power cannot be more than 1 because it is the ratio of the energy absorbed to the total energy. You are not going to absorb more than you receive. So this is value is equal to or less than 1 for always. So do you have any doubts up till now? Is there anything? Is there anything? No? Great. Now let's look at certain quick questions. Which of the following is the fastest process of heat transfer? Yes, radiation is the fastest process. Why? Because it radiates. It radiates in a form of electromagnetic waves. And when it is an electromagnetic waves, speed would be 3 into 10 to the power 8 meter per second. It is same as the light speed. Light wave is an electromagnetic wave. So you could not travel faster than the light, and so heat could not travel faster than the light. So radiation is the fastest process among conduction and convection. I hope this is clear. Next, human emissivity. Yes, it's a 0.97. Human emissivity is about 0.97. One, one. It's an emissivity of black body. This is emissivity of black body. 0. It's a emissivity of perfect reflector. Next, the absorptive power cannot be greater than 1. Yes, because it is the ratio of the power that is absorbed to the power that is being available. That means power that has been available. I hope this is clear. Is it clear? Any doubts? Is there anything? Anything? Are you sure? Great. Now let's understood Kirchhoff's law and its applications. Let's begin with Kirchhoff's law. According to the Kirchhoff, at a given temperature for a given wavelength range, the ratio of the emissive power to the absorptive power of a substance is a constant. So basically he says that emissive power to the absorptive power is constant. E lambda by L lambda is equals to constant. And this constant this constant is equals to the emissive power of a perfect black body at the given temperature and the wavelength. So this is E lambda by A lambda, that is equals to constant, and that is equals to the emissive power of a perfect black body. So thus we understand that E lambda is directly proportional to the lambda. Being good emitters, they are good absorbers of the thermal radiations that we have. Now we understood this in a form of the Kirchhoff's law, but even previously we understood that if anybody is having an higher amount of E, then it must be an higher amount of A. We have derived this. It's an A is equals to E. Yes, this is has been derived in our analytical way, that has been now derived, that has been now been given, and that has been now concluded in a form of the Kirchhoff's law. Please do remember this. Let's look at the applications of this. So Fraunhofer lines in solar spectrum is an example of the absorption spectra. Our cooking vessels are coated with black outside, since black surface is a good absorber, and when it is going to absorb everything, it is going to emit everything. So Fraunhofer lines can be explained by the Kirchhoff's law, and we understood one more thing, that highly polished surface are very good reflectors, but they are very poor absorbers. This is again the same thing, that if your A is higher, your R would be the lower. That means if you are very good absorber, you are very poor reflector, and vice versa of this is correct. Yes, do you understand this? Do you understand? Have you have you understood this? Any doubts up till now? Let's look at the quick questions. It says that a block of ice, yes, it can radiate as well as absorb the heat. A block of ice is going to radiate as well as it is going to absorb the heat. Next, a Fraunhofer lines in solar spectrum. A Fraunhofer lines in polar spectrum can be cited as an example of, yes, it's an example of Kirchhoff's law. And next, in a case of perfect black body, in a case of perfect black body, its emissivity would be 1. Yes. Its an absorptive power would be 1. Yes. It's a reflecting and transmitting powers. It's a reflecting and transmitting powers are 0. Yes. So all of the above are correct. I hope this is clear. Is it clear? Is it clear? Are you sure? Are you? Do you have any doubts up till now? Is there anything? Is there anything? Any confusion up till now? Do you have any confusion? No? Great. So, shall we switch to the new law? Shall we? Can we? Great. Now let's look at this. It's a Stephen's law. Now let's look what Stephen has said to us. That Stephen's law, this is, he says that the radiation emitted by a black body per unit area per unit time is proportional to the fourth power of absolute temperature of a body. It's an absolute temperature. Or he says that the emissive power of a black body is directly proportional to the fourth power of its absolute temperature. So when I say this, it's an emissive power, I represent E as the emissive power, which is directly proportional to the fourth power of the absolute temperature. If I remove this proportionality constant, uh, I can add I should add one proportionality constant, and I have added as a sigma. This this sigma will represent at E is equals to sigma into T to the power 4, and when I write E, it is basically a Q by A into T. It is basically a Q by A into T is equals to sigma into T to the power 4. I hope this is clear. Yes, is it clear? This is Q by AT. Q by AT is equals to sigma into T to the power 4. So when this was the situation that, let's suppose only a body is there, only a body is there, and this body is at temperature T, then what amount of emissive power it is going to deliver? Then we said it's an E directly proportional to the T to the power 4. But now let's suppose this body has been put up in certain environment. It is something like this, that this body is at temperature T and this environment, it is at temperature T naught. Then this power P could be written as it's a minus of E sigma A into T of object to the power 4 minus T of the environment or T of the surrounding to the power 4. Please note this sigma is the constant, which is what we call as a Stephen's constant, and its value is the 5.67 into 10 to the power 8. You can remember this as a 5, 6, 7 and 8. It's a 5.67 into 10 to the power minus of 8. This is E is the emissivity, that now you have very clear idea about the emissivity, and A is the surface area of an object. A is the surface area of an object. I hope this is clear. So this is the situation that Q by T, this is equals to P, this is equals to sigma into A into T to the power 4. Value of sigma, it is 5.67 into 10 to the power minus of 8. So watt per meter square per Kelvin to the power 4. And unit of Stephen's constant, that is, here it is, dimensional formula, it's an m1 L0 T to the power minus 3 theta to the power minus of 4. It's a Kelvin to the power minus of 4. I hope this is clear. Is it clear? Is it clear? Do you have any doubts? Is there anything? Anything? Are you sure? Great. So the radiative power for any body is given as P is equals to E sigma A T to the power 4. When a body of radiant power P is kept in an enclosure of P naught and at temperature T naught, this rate of heat lost could be given as E sigma A into bracket T to the power 4 minus T naught to the power 4. I hope this is clear. Is it clear? So what you are supposed to do is you just think in that manner, that if I have been given, let's say if I have been given this is body, this is at temperature T, find out radiant power of this body. What I need to do, I need to go for this. But if I am supposed to be given something like this, that this is body at temperature T and it has been put in a temperature T naught, in a surrounding temperature is T naught, then what you are supposed to do, you are supposed to do this, it's a T4 minus T naught to the power 4. Yes. So if both the temperatures has been given, you are going to go with this. If only one temperature is given, you need to go with this. It is as simple as that. I hope this is clear. Is it clear? Is it? Great. Now let's suppose we have a two bodies. One of the body is having a surface area A1, another body is having surface area A2. One of the body is having, it's kept at the temperature T1, another body kept at the temperature T2. If I want to find out the ratios of the heat radiated by these bodies, then it would be a P1 is to P2. Basically the simple formula is that P is equals to E sigma A T to the power 4. So when I write it's a P1 is to P2, when I write P1 is to P2, it is basically E1 is to E2. No need to write sigma 1 is to sigma 2, because sigma is a constant and it is going to be cut it down. So it's an area 1 by area 2 into T1 to the power 4 divided by T2 to the power 4. Please mind well, this T must be in Kelvin. In examinations, in data providing, during the questions, they will give you in the Celsius. But if they have given you in the Celsius, it is your responsibility to convert it into the Kelvin and then go for the formula. So it is basically, first you need to attempt in maths, and then you need to go for the physics. I hope this is clear. So first you need to convert it convert it to the Kelvin, and then go for the question answers. Please do this. Don't ever forget. Don't ever forget to do this. So if the bodies are spherical in shape, let's suppose these two are the spheres and their radiuses are given, it's an r1 is to r2, then the area 1 could be written as 4 pi r1 square and area 2 could be written as 4 pi r2 square. So if I'm taking the ratio, this 4 pi has been cancelled, and this p1 is to p2. This is equals to e1 is to e2 into r1 by r2 whole square into t1 by t2 to the power 4. This is the situation when only the body has been given at temperature T. Now let's understood that what would be the situation. What would be the situation when it has been kept in the surrounding, that the ratio of the initial rates of heat lost by two bodies kept in the same surrounding. So it is something like this, that this is the surrounding, and now this is at T1, this is at T2, this surrounding is having a temperature T0, this is given as a radius of R1, this is given as a radius of R2. So their rates of the heat lost could be given as R1 is to R2. This is E1 by E2, A1 by A2. Now they are the T1 to the power 4 minus T0 to the power 4 divided by T2 to the power 4 minus of T0 to the power 4. I hope this is clear. And if they are perfectly spherical bodies, then I could write it's an R1 by R2 is equals to E1 by E2 into R1 by R2 whole square into bracket T1 to the power 4 minus T0 to the power 4 divided by T2 to the power 4 minus of T0 to the power 4. This would be the ratio of the rates. I hope this is clear. Is it clear? Is it? Are you sure? Are you sure? Any doubts up till now? Is there anything? Is there anything? Are you sure? Are you? Great. Let's look at the quick questions. It said the amount of heat radiated by a black body per second per unit area is blank to the fourth power. Yes, it's an amount of heat absorbed by radiated by a black body per second per unit area is directly proportional to the fourth power of its absolute temperature. This is directly proportional. Yes. Next, the value of sigma. Yes, sigma is the Stephen constant. It's 5, 6, 7 into 10 to the power minus of 8. So it's a 5.67 into 10 to the power minus of 8. Dimensional formula of Stephen's constant. How can you how can you calculate it? What do you think? Basically, this is the P is equals to E sigma A T to the power 4. E is the dimensionless. Now P, basically that P is the energy divided by area into time. This is equals to sigma into A into T to the power 4. Now from this you can derive this very easily. I hope this is clear. Is it clear? Do you have any doubts up till now? Do you have any doubts? Is there anything? So now are you ready for the questions? Are you? Are you ready for the questions? Great. Let's have a look. If a body is at a temperature of 927 degrees Celsius, find out what amount of energy it can radiated. So this TC has been given as a 927 degrees Celsius. This was the question that have been asked in the certain AIPMTs. Because as an faculty, I understand that a student is going to write something like this. It's a basically a multiple choice questions would be there. So definitely a four option would be there, and one of the option, and it was the first option that was this. So please do not go for this. We must remember that this is E directly proportional to the T to the power 4. And that's why what I need to do is that I need to convert this. It's a 927 plus 273. This is equals to 1200 Kelvin. So this amount of energy radiated would be proportional to the 1200 to the power 4. Yes, this would be the correct option. uh, Many other questions has been asked. This radiation is having a very high probability to be asked. Even if you see the J mains that has been started by NTA and that is conducted online. Yes, if you see every sessions of the JE mains examination, you will find at least two questions from Stephen Boltzmann. I hope this is clear. So this is very very important. Let's work for the next question. Please keep this in mind. Please do not forget it, that we cannot use temperatures in the centigrades. Fahrenheit, they are not going to provide us. But if they will provide us in Fahrenheit, I will convert it to the Kelvin. So first convert it to the Kelvin. First convert it to the Kelvin, and then switch to the physics. I hope this is clear. Now let's work for the next question. The question says that two bodies having temperatures are 127 degrees Celsius and 227 degrees Celsius, having radius 2 meter and 4 meter, having radius of 4 meter and 4 meter. Find ratios of their radiating energies. Assume that bodies are spherical. So how will you do this? What is supposed to be done with this? What do you think? What all they have given? Let's first write this. It's a T1 that is given. It's a 127 degrees Celsius. Convert it to the Kelvin. It's a 127 plus 273. That means that is 200 plus 200. It's a 400 Kelvin. T2 is given, that is of 227 degrees Celsius. So it's a 227 plus 273. This is 300 plus 200. This is a 500 Kelvin. And the radiuses are given, that R1 is equals to 2 meter, R2 is equals to 4 meter, or I should say, let's say, write this, it's a two identical, or remove this identical, create a confusion. Let's add it here. Yes. That assume that bodies are spherical and made up from same material, and it has been made up from the same material. So their emissivity is given, that is E1 is equals to E2. So this is all they have provided. What I need to do, I need to find out the ratio of the radiating energies. So let's do it. This is basically E1 is to E2. This is equals to E1 A1 T1 to the power 4 divided by E2 A2 T2 to the power 4. They have given E1 equals to E2, so this has been lost. It's a 4 pi R1 square multiplied by T1 to the power 4 divided by 4 pi R2 square multiplied by T2 to the power 4. This 4 pi and 4 pi has been gone. Now let's find out the ratio of the radiuses. This is 2 square 4, 4 square 16 multiplied by T1 to the power 4. It's a 400 to the power 4 divided by, it's a 500 to the power 4. So this could be this could be solved as an E1 by E2. This is equals to 4 by 16, 1 by 4 multiplied by 4 to the power 4 divided by 5 to the power 4. So this is equals to 4 to the power 3 divided by 5 to the power 4. 4 to the power 3, it's a 4 square 16 and 4 cube 64. 5 to the power 4, it's a 625. So this is the ratio. It's a E1 is to E2. I hope this is clear. This is clear. Is it clear? Is it clear? Is it clear? Do you have any doubts in this? Is there anything? Is there? Do you have any doubts? No? Any doubts? No? Great. Now let's work for the next question. Let's suppose let's suppose they have asked us that two objects having temperatures at 927 degrees Celsius and let's say 727 degrees Celsius respectively. It's a two identical, yes. So two identical objects having temperatures at 927 degrees Celsius and 727 degrees Celsius respectively have been placed in same surrounding which is at 27 degrees Celsius. Find ratio of their radiating power. What will you do? So let's summarize. First, it's a T1 that has been given. It's a 927 degrees Celsius. So that is need to be 927 plus 273, that is 1200 Kelvin. Second, it's a 727 degrees Celsius. This is 727 plus 273. This is 800 plus 200. This is 1000 K. Our surrounding temperature is given, that is at 27 degrees Celsius. So that should be 27 plus 273. This is 300 Kelvin. They have said two identical. When they said identical, their area will be equal because the radius will be equal, as well as they have made from the same material, so their emissivity would be equal. So what I'm supposed to do is that first I need to take a ratio of this, and when I need to take a ratio of this, what I understand is that it is something like this. Let's have a look. It's let's call it as a P1 is to P2. This is equals to E1 A1 T1 to the power 4 minus T0 to the power 4 divide by E2 A2 T2 to the power 4 minus T0 to the power 4. This has cancelled, this has cancelled. I have been left with this only. So this is equals to, T1 to the power 4. This is equals to 1200 to the power 4 minus This is T naught. It's a 300 Kelvin. 300 to the power 4. Divide by. Divide by. This is equals to 1000 to the power 4 minus minus. This is equals to 300 to the power 4. Yes. So now, can you write this? Look at this. This to the power 4. That means this 12 into 10 to the power 2 and to the power 4, and this would be gone. It's a, let's say it's a 10 square to the power 4 into bracket 12 to the power 4 minus 3 to the power 4 divide by. This is again 10 to the power 2 to the power 4. This is equals to 10 to the power 4 minus 3 to the power 4. So this has been cancelled, that you understand. Now, can you do this? This P1 is to P2. This is equals to 12 to the power 4 minus 3 to the power 4. This is 9 to the power 4. Divide by 7 to the power 4. Can I do this? Can I? Can I do this? If you are doing this, you are absolutely incorrect. This is not to be done. Please, please, please take a pity on the maths and please don't do it. Please, it's a request. This is not the way to do this. It's a P1 is to P2. This is equals to 12 to the power 4 minus 3 to the power 4 divided by 10 to the power 4 minus 3 to the power 4. I hope this is clear. So this is to be done. This is to be done as a separately. You can do this. It's a 12 square plus 3 square into bracket 12 square minus of 3 square. Yes, this is absolutely correct approach. It is basically a square minus of b square, so it's an a plus b into bracket a minus of b divide by this is 10 square plus 3 square into bracket it's a 10 square minus of 3 square. So this is equals to this 12 square, it's a 144 plus 9 into bracket 144 minus of 9 divide by it's a 10 square 100 plus 9 it's a 109 into bracket 100 minus 9 it's a 91 and something like this. This is equals to 153 multiplied by 144 minus 9 it's a 135. Yes, divide by 109 multiplied by 91. So this could be done and this would be the ratio of their powers, but please don't do this. This is not the way to do it. I hope this is clear. Is it clear? So do you have any doubts? Do you have any doubts? Do you? No? Let's work or let's understand and let's summarize the radiating capability when we are having at P. This is equals to E sigma A T to the power 4. So this radiating power depends on first it's a material of substance because it depends on the E. Second, it depends on the surface area. It depends on the surface area. P is directly proportional to the A. Higher the A, higher the P. And third, it depends on the absolute temperature. That P is directly proportional to the fourth power of temperature. So higher the temperature, higher the power, more the surface area, more would be the radiating power, and value of E should be higher. That means if E is equals to 1, it is the perfectly black body and its emitting capability would be the maximum. And if emitting capability is maximum, its radiating power would be the maximum. I hope this is clear. Is it clear? So do you have any doubts up till now? Is there anything? Is there anything? No? So let's wind it up this session over here. This was the first part of a radiation, because we have not completed the radiation yet, and certain laws and certain theorems has been left in radiations. So what I want, before you switch on to that video, please go through this, have a practice of this, go through every theoretical parts as well, because even from this unit a theoretical questions has been asked about the black body, about the radiating power, about the emissive power and all that. So please go through this, revise it well, practice it well, and if you practice it well enough, if you practice it good enough, this will a sure shot question for us, because these are the questions which are not having a very higher amount of applications. Yes, a limited applications are there, a limited variables are there, so this can be done very easily. Please understood this fact and go for it. Please revise it thoroughly. This will help us. Thank you. Have a good day. Take care. Bye bye.